Good afternoon, everybody. Thank you for taking the time to sit in with us today. We're just going to do a kind of a high level on some different um, stereolithography materials. We're going to briefly at the beginning talk a little bit about the history of SLA and how we got to where we are today as it pertains to the material side of things. And then we're going to talk about some applications after each one of the materials that I get into. So we're going to just kind of jump in, get going here. Again, thanks everybody for joining us today. And let's start with a real brief history of RP America. We're located in New Sharon, Iowa. And RP Support was founded by Dan Turstrep in 2011 to provide support and service for stereolithography equipment across North America. In 2016, we began RP Sales America, and we started selling Union Tech stereolithography equipment, and that is open source for materials, so it really lends well into what we do here with our materials and what we're going to be discussing today. We're founded on values of hard work, integrity, and strong relationships. For those of you that have spoke to us, you should be familiar with our relationships and how we really work with the customers best we can. This is just a couple of pictures. The bottom left here, this is actually the shop. Our building resides actually on the farm of Dan, so we're kind of out in the country. This picture up on top here, this gentleman is Sean, who's driving the tractor. He works for Unitech out of China, and him driving that tractor is the first time he'd ever driven anything with four wheels. So we'd like to share that a little bit. Also on the farm, we like to have fun and enjoy ourselves, so we get some fishing and things done like that out back. So if you ever get an opportunity to come here, we'd love having customers come to the shop and see what we're all about. So little first here, did you know stereolithography? So the first 3D printing technology, it's come a long way over the last 30 years. It's now one of the most versatile technologies available. I feel that material sciences have now caught up to what the technology is capable of. So stereolithography has been around for 30 years. Yes, we know that. And the reason we're going to talk in the beginning here about how we got to where we are and what the materials used to be like is there's still a misconception out there that stereolithography materials and the process can give good prototyping results and functional parts. So that's really what we're here to talk about. So SLA, SL, and DLP. What is really the difference here? So stereolithography, or SL, is the typical abbreviation. Most people are familiar with SLA. That term is trademarked by 3D Systems, and it stands for stereolithography apparatus. DLP, that's digital light processing. It's very similar to stereolithography, except that instead of a laser drawing each area of the model itself, the DLP will actually project an entire image all at once. So how stereolithography works? You have CAD drawing. That's the first part to pretty much any 3D printing operation is you need to have the CAD file. Then we take that CAD file, typically STL, and we will take that into the slicing tool, which will generate support structures as well as break that model down into individual layers. We use a 355 nanometer laser, and that hits a mirror, which we call the scanning system. And then that scanning system is what actually draws the part. So each layer that's created, the platform will actually drop into the vat of liquid. A recorder blade will sweep across and level out the liquid as well as remove any air bubbles. And then we just repeat the process. And we do that until it's finished. And when it's done, the part automatically just raises up out of the liquid and starts to drain. So the foundation years, we're going all the way back to 1982. Acrylate-based formulations were the norm back then. They required speed of reaction and overall cure to generate the properties for early stereolithography. The materials were usually very highly viscous, so they were really thick, and there were complications that come along with viscous materials like that, so the recoating challenges and things like that. There's also problems with shrinkage, curling, or distortion. Large parts were not very accurate. across a wide range or a large size. So part accuracy was kind of a problem. Poor strength of the laser cure. The resins, you know, we were really starting to understand how the process works. So we ended up having poor green strength. The parts were very brittle. Acrylate chemistry in general is a difficult process, difficult chemistry to get accurate and keep accurate. So that's kind of how it started. And this is really a big part of the misconception moving forward. Stereolithography, generally people think that it's really expensive and the parts don't last. If the part gets knocked off the table, it's going to break. That was the case in 1982. That's no longer the case at all. If I am presenting in front of people, this is where I'll take parts and literally throw them on the floor. They hold up, they're durable. Different materials have different properties, and it just all works out better. So as the years progressed, we get into 1993 timeframe. We get into these epoxide acrylate hybrid materials, and you can kind of see here the physical strength and the physical properties greatly increased when we get into the epoxy based resins. So then we move into the expansion years. We get starting to really understand what the chemistries can do for us, and trying to mimic materials that have the properties of thermoplastics, like ABS for injection molding. If you're not terribly familiar with ABS, that is Legos. That's the #1 thing that people will think about when you think about ABS. Also, we can get into now clear and colorless materials, expanding the capabilities in fluid flow behavior analysis, allowing people to see what's going on or turbulence inside of clear parts that are used for prototyping or material development. Then the composite materials begin to emerge at this point as well. We're going to talk a little bit about composite material here in a few minutes. So we're moving toward that engineering thermoplastics. That's the goal. So they developed what's called an X class, which is kind of like the next version, or they were really shooting for greater material properties, and so that's where this X class kind of develops from. We're creating materials that have very tough properties, high impact resistance, also decent elongation. ABS is more stiff, so we have a little less elongation, okay impact type of resistance. But when we get into that X class, now we're talking about really good elongation and good impact resistance. So this is just a little graph kind of showing the flexural modulus as well as the tensile elongation at break. And you can see if you want parts that are not flexible but have a really good temperature resistance, now we're looking up in the those composite materials. If you're looking for materials that have a much less flexural modulus but are really good in the tensile strength, then now you're talking like a polypropylene-like materials, and that's there's just all kinds of materials. There's a wide range out there for things you can see. So these are some of the materials we're going to be talking about today. First, I'm going to discuss some of the DSM materials. We're going to talk about Evolve next. A couple of the clear materials, 11-122 and 10-122. Taurus, which is a great new and up-and-coming material. And Perform. Perform's been around for a while, but this is one of those materials that have an additive that actually give a lot of strength and different properties. Then we're also going to talk about a couple of new players out there. BASF has a great new material, and Adaptive 3D, tough rubber. And when we get to that, we'll discuss that a little more as well. So let's jump in here. First, we're going to talk about Evolve. So we have some good material properties here. You can see we have really nice tensile modulus, elongation at break, 11% is not too bad. Good temperature resistance as well. 126 degrees Fahrenheit's not bad. It's not going to withstand under the hood type of applications, but most prototyping applications it'll be just fine. So here's an example of Evolve actually being used. So this is a print that came off of one of our printers, our 600 platform, And this was a customer of ours that was doing a prototype for a company. And so they actually built that on our platform. And when I first saw this image, I thought it was just a CAD rendering, and turns out this is a physical picture of the part after it was painted. So printed, cleaned up, painted, and here it is in the full assembly prototype. And what's interesting about this particular assembly prototype is if it is plastic, any of the parts on this prototype that were plastic were actually printed, including the wheels. So the wheels themselves were printed. The shaft or the axle that holds the wheels, that's obviously not. The handlebar, that's metal, that's not. The cables are not. But every other component on the inside that is actually plastic has actually been printed on this part. So functional prototypes, just to open your eyes a little bit, think about how things can be done. Large sizes, very capable. Our 600 is around a 2-foot platform, so you're roughly, it's 600 millimeters is what that 600 represents. So 600 by 600 in the XY. Next, so this is part of that X class of materials. And so we're getting the best of both worlds here. We have good tensile modulus, we have really good strength at yield. The elongation is a little less, but the temperatures are getting higher. So the impact resistance is also really good on this as well. That image there with the hockey sticks, those are actually 3D printed blades, and you can use them to play hockey. They're that tough, and they will hold up. Here's a really simple example. We have a little guide here for a router. This company, Gulfstream Aerospace, had been using wood router guides for a long time, but as they would age, the more they would get used, they'd loosen up and just become not as effective. So they actually used this next material and printed a guide, and they're much more robust. They hold up longer, they last longer, and less wobble comes out of the router guide itself. So just an interesting tooling application I wanted to throw out there. I like this one because I like beer. Here we have some brewery tappers. All of those white tappers you see are the traditional methodology. They're created with ceramic in a mold. They've got a foam core. They're all hand painted, and typically, after 2 to 3 months, they need to be replaced because of the wear and tear in the use. So there was a customer of ours, a service provider, that actually was approached by these guys and pointed them in a direction. So in 1 week, they had a sample. That's the green part there, the green with the purple top. They had a sample within 1 week. That's from CAD through printing. After 6 months of constant use, it's still on tap. It's still being used. The bartenders love it. It doesn't chip. It's been very durable and held up. So we're almost talking about past the prototype stage here. We're into real production or actual production parts. All right, let's talk a little bit about some of the clear materials. This first one is 10122. So this has got good strength. The elongation of break is not nearly as, this material is not nearly as flexible at 7.5%, but it's got decent impact resistance. And this material can be thermally post-cured, and you can see the increase for the HDT from 117 up to 140 by running through a thermal cure. Some examples of what this would be used for. This would be good for fluid flow analysis, the concept and functional models. It's also really good refractive values out of this material. This can actually be used as a lens and polished and actually do optical light testing or transmission work there. So the process, there's different processes of making these extra clear. A little bit of elbow grease, some wet sanding usually, and a little bit of clear coat. Even just a clear spray clear coat works really well and really makes these things pop. So post-processing is really not too complicated. Here's another clear example. This is called 11122. The name watershed actually is a little indicative because it means that it repels water. It does not like water. It's really used in casting industries a lot. They'll print materials because in castings, when they're doing the burnout, there's no moisture left over. So it works really well. Good tensile modulus here. You can see about twice as long as on the elongation of break. A little higher temperature in its net state. So just a good all-around material here. That lens in that picture, I've actually had my hands on that. There's 3 separate printed parts there, and the clear part's really just been clear coated, sanded and clear coated, and has great refractive values. Here's an example. This is actually what the part would look like, very similar once it's come off of the machine without any polishing happening. It's still pretty clear, but Roush Yates, they actually use this material extensively when they're doing new design testing. It allows for a much faster process to get machines just understand what they want the geometry to look like without having to run castings and patterns and go that route. They can print the parts, they can make changes, reprint them again. Because it's got the clarity, you can actually see what's going on, so they can make those internal changes as well without having to do cutaways. They can bolt these things up and actually run on the engine. So in this example, it's cut the design time as much as 45%, and that's really big when you're in a race to get to market before your competitors. Taurus. This is a newer material. This came out in 2017, yeah. So this material was actually developed in conjunction with Toyota Formula One Racing, and the reason this material was created is typically you have high temperature resistance, but you'll get low impact resistance, or the other way around, you'll get high impact resistance, which drops your HDT on the temperature side. This material was kind of designed to be more in the mid-range of both of those. So we're actually bringing up the tensile modulus is higher, the HDT is higher, good elongation of break. So there's a lot of good applications for this material, internal, externally, all around. It's just a really good material for prototyping. It gives superior strength and durability, a wide range of applications, excellent surface finish. Here is a little intake under the hood application from an automotive side. Here, another automotive example. This is an interior application. That's actually an armrest that would be mounted to the door. And then the bottom one's just a close-up showing what the surface finish can look like, and without a whole lot of effort or post-processing. Perform. So this is a composite material, and really high tensile modulus. This material is incredibly strong. It's used very widely in Europe in wind tunnel applications because of how stiff it is. So that's one example of a great opportunity to use this material. But it also has really high thermal resistance as well. Simply, the ceramic additive in this material it really helps with those types of applications. So here's a little example. This was a Formula One college racing team that was struggling to find a material that was going to hold up to this particular application. Under the hood, 200 degrees Fahrenheit, they need to be able to do that. They also had some carbon fiber runners that would soften as they approached 175 degrees. So they needed a material that was going to be able to do better than that. So Interpro is a customer of ours, and they suggested using Perform because of its high temperature resistance and ability to withstand great stresses. So these parts here, they were printed overnight on a high resolution stereolithography printer. They were bolted to the engine and run through dyno test to measure the horsepower. And during hours of high RPM engine testing, these parts work perfectly. So we're talking about now parts under the hood in applications where you have high temperatures, and these thermoplastic parts, they hold up. So just a great example there. Another great opportunity for this material is in low volume or short run injection molding inserts. I've been pushing this a little bit. I may have even talked to some of you out there regarding this, but this is a great example. This is a mold for a switch. It's a polyamide 6. and it was shot at 270 degrees Celsius. And this mold was able to produce 47 pieces and was fully intact with only just a couple of small little edges breaking off after that many shots. If the parts are simple, you can still do a mill or a mold that can make sense. But if the part gets more complex, then additive is definitely a way to go. And this material provides opportunity to do that. You think about the additive manufacturing can speed up the process 1 to 2 weeks compared to 5 to 7 weeks. You could run through multiple iterations in this process before you'd ever get your first mold that was cut. So we actually are dealing with a couple of customers right now that are very highly interested in this. We've done some examples where they were injecting a Velox material that had a melt over 500 degrees, and we were using these mold inserts, and they performed flawlessly. Sometimes a little bit of post-processing is required, a little polishing of the parts helps. But other than that, if you use a little bit of mold release, these parts come out great. You do have to, it's a slower process. Typically you're blowing air on the molds before or after each run, so it could be a minute in between cycle times. But when you're only doing 30, 40 parts, because that's all you need, then that time's not too bad. This last page here I want to talk about. This is a product selection tool from DSM. This is actually on the web, and I just want to bring this up real quick and show you what this looks like. So what we have here is a nice little graph, and when you mouse over one of these materials, it tells you the physical properties of those materials. Now, we're looking here at our flexural strength as well as the tensile strength. If you come up here, you can adjust these parameter settings and adjust to any of these in the X and Y. So it gives a real good opportunity to understand, if you're looking for very specific properties, this can help you when you understand that. You can also compare different vendors. So if you want to compare it to, say, 3D Systems, what that material looks like, so you can see where their materials fall compared to maybe DSM's materials. Now, again, this is only just an example. I just wanted you guys to be aware that there are tools like this out there, and DSM has a great tool for understanding what this can look like. Okay, so next we're going to talk about material from BASF. This is a new material. It was actually first released this year, and it's got this is a urethane-based material, so it acts a little bit differently, but the end results end up the same. You get good parts, whether they're prototype or functional sample parts. Good impact strength, good build speeds. They can be transparent. You can use colors as additives. They can be painted, like all SO parts can be painted. Good thermal and UV aging stability with this material. This material also can be used at different levels, different wavelengths of cure. So it could be used for a high-end professional machine at 355 down to a lower, like a Formlabs type machine would work with this material as well. A couple examples, or actually this is just some material properties on this material. Good tensile strength, not too bad HDT, and flexural is not too bad as well. Here's just a couple of simple little examples. We have good impact resistance, dimensional stability is really good, thin walls, high detail as possible. Just a couple examples here, a gear. This is a foot pedal for a bike. That's a clip for like a strap, so you can see that the flexibility is actually there too. Some electrical connection. If you're looking for some custom electrical connectors, just a good example for that. An impeller and a propeller, kind of showing just the fine detail and clarity you can get. Functional and prototypes, performance, good fit and form for demos, jigs and fixtures. It's a really good application for that as well. Okay, adaptive tough rubber. This is a new player. This material first became available in I think it was April at Rapid TCT this year down in Texas. And this is a really interesting material. We're really excited about this material and what types of applications it can be used for. We have really good tensile modulus, and the important piece here is the elongation of break, 450% elongation of break. Got a Shore A hardness of 90, which is really pretty good. This material does not act like an elastomer where it just responds immediately. So when you actually compress this particular version of this material, it takes a little time for it to rebound back to its original shape, but it always does. We've pushed on this material pretty hard and contorted it. I've actually seen sheets of this material that you can't even tear. You're just a little less than a millimeter thick, and you can't even tear this material. It's such a good material for a lot of applications. Here's a little example. That's actually the CEO of the company stretching that material to show what that actually, the type of flexibility you can get out of that material. A few more potential applications here. So for material to have rubber-like properties and additive, you're looking for a strain of greater than 300%. Needs to have a good tensile strength on it, and appears and feels like actual rubber. And this material does. Applications: custom rubber gaskets, boots, shock absorption of some kind. Simulate overmolding, so you could actually print this and either glue it or maybe stretch it around the handle to give a good overmold opportunity. And we're really starting to understand what we can do with this material and types of applications. So, I asked the question, what can you guys think about if you could have an on-demand material like this? What can it do for you? Here's another quick thing. We're going to talk a little bit about metal cladding. Stereolithography, because of its surface finish being so smooth, lends itself really well to being metal cladded. So you can structurally reinforce parts. Here is a couple applications. It's not just for strength, but appearance as well. So thermal and electroconductivity, so you can plate it in just copper if you want. You can add nickel to it, which is going to give it near die cast strength properties, which is really impressive. I actually have a sample part that I like to stand on and show people that this is a plastic part underneath, but a little bit of metal plating and the part becomes incredibly strong. Also good for EMI shielding, good environmental barrier for chemical resistance, outgassing prevention, abrasion resistance. You can think about it as a wear indicator potentially if you're looking for some unique applications for that. Just durability, the impact strength, again, die cast properties out of this material. Here's a couple applications. The one on the left, that's in the International Space Station, and they use it for once the part's been plated, it's not flammable, so that's really important, especially in the space application like that. Good strength as well as some emission resistance as well. On the right, that is a custom gas tank, and so an accent for the gas tank, and just a little bit of polishing, and you can see to what level you can get to. This particular one, those are the initials of the end user there. So that kind of takes us to the end. So we look forward to seeing more people, and hopefully we can actually see you again very soon.